For the first time, humankind could witness stars being formed, as perhaps the sun, our star, once was. We could watch distant galaxies, hundreds of millions of light years away, collide. Or in a supernova, see a bright star die out in a massive explosion of gas and light.
There is one picture that Hubble provided which really sticks out in my mind. It's called the deep field. Hubble looked at a small part in the sky where there were not any stars and integrated the light for many, many, many hours. It pulled out all these very faint galaxies.
New galaxies in a completely pitch dark spot in the sky, just as big as your thumbnail. It's phenomenal what we started discovering with Hubble.
Hubble made a major leap forward in really showing the magnitude of the universe. I mean, there are at least 100 billion galaxies. And each galaxy has hundreds of billions of stars. And the farthest galaxy that Hubble has detected is over 13 billion light years away. It's absolutely amazing.
And then, hanging in this very immense universe, alone in the vastness of space, that tiny blue marble we live on.
When we look outward, when we understand the planets, when we go out into the universe, we're really still trying to look back at ourselves and say, how does our planet work?
The Earth is a water planet, with oceans covering more than 2/3 of its surface. The Pacific is the largest and deepest. For NASA, the oceans, like the ice sheets, provide essential insight into our planet's well-being.
NASA's Earth Science program has played a key role in understanding what the health of the oceans is. We know that coral reefs are a critical part of the ocean ecosystem. A lot of people think, well, coral reefs are pretty and brightly colored tropical fish live around them. But they really are the canary in the coal mine as far as the oceans are concerned.
NASA's Coral Reef Airborne Laboratory monitors coral from Australia to Palau to the Hawaiian Islands.
This is the last day of the Hawaii campaign. We'll have 11 a.m. go, no-go call.
So we're gonna do a site here and then we'll scoot over there.
We also have to do on the back reef, the coral-rich areas, right?
Right.
The coral mission relies on the Portable Remote Imaging Spectrometer, or PRISM. PRISM is an instrument that sees 200 colors, RIC3. We fly at 28,000 feet over a reef. We're gathering data on reef condition and feeding that information into a computer.
The oceans are also being studied from NASA's Earth orbiting satellite systems. NASA is the only agency that designs and builds and flies the satellites, and then we share the data with the world. Really, if you want to get precision in terms of your scientific measurements, you need to fly in the air and then get the satellite data, and then you need people on the ground.
have teams that go in the water to validate the airborne data. Coral reefs respond quickly and dramatically to changing environmental conditions. When corals become stressed, it looks like somebody poured bleach on them.
The coral reefs are bleaching and dying. In 2016, just in 1 year, we lost 30% of the world's corals. This is primarily caused by temperature rise. The oceans are really heating up.
The water is getting warmer and warmer. Part of our mission to study this planet is to understand why.
How is the exchange between the land and water surface and the atmosphere changing? And how is carbon dioxide going to feed back to the climate system?
Carbon dioxide acts like a blanket. What happens is the sunlight comes down through the atmosphere and it warms the surface of the earth, the oceans, and the land. And then they emit heat. And carbon dioxide in the atmosphere absorbs some of that escaping heat, warming the atmosphere and warming the planet.
Carbon dioxide is a natural part of the atmosphere. It helps keep the planet at a comfortable temperature. But what might happen if the amount of carbon dioxide in the atmosphere increases?
The planet Venus. Although the same size and density as Earth, the similarities end there. Earth has water and light. Venus is desolate, dry, apparently lifeless.
One of the key questions for scientists in the early 60s was, why was Venus so hot? We didn't know what was in the atmosphere. Carl Sagan famously said it must be because there's so much carbon dioxide and there's a massive greenhouse effect.
Venus may have been the first habitable planet in our solar system with a significant amount of water and all the right energy and all the right chemicals as a terrestrial planet to have supported life. Because of data we received from the orbiters that we launched and landers that went down to the surface, we learned that it was indeed carbon dioxide that had created what we call a runaway greenhouse effect. And now, the temperature on the surface of Venus is hot enough to melt lead. Could what happened on Venus happen on Earth? When we study the solar system, we're also looking at how it evolves over time. And we want to know the conditions on each and every one of our planets. Places like Venus were much more Earth-like in their past. Mars was much more Earth-like in its past. Those two planets could have harbored life.
We knew from previous missions that water, liquid water, had been on the surface of Mars. But was it salty or sweet? Was it acidic or basic? Essentially, was the ancient wet Mars habitable? Could it have supported life? That's the question that Curiosity was sent to answer.
The complexity of the Curiosity rover, in terms of being able to get samples and analyze them, is really amazing. What we basically gave it was an analytical chemistry lab. It's really the first time we've had anything like that on any planet. It drills into the rock, makes powder, and then is able to drop it off into some inlets where instruments can then do more complicated analysis. What Curiosity was able to find, even fairly early in the mission, was types of rocks that only form in water over long periods of time. It was able to find minerals that indicate that that water was persistent and that that water is the kind of water you could reach down and take a drink out of. And that is one of the holy grails of habitability.
Curiosity has answered our question, and that answer is yes. The ancient wet environment, 3.5 billion years ago, when life was first starting here on Earth, Mars was an environment that was habitable for life. So that's pretty darn cool.
Mars was once a habitable planet. But as NASA has shown us, planetary bodies are not constant. Over time, their environments can transform in ways that might make them inhospitable to life. Space has proved to be a dangerous and unforgiving place. Still, NASA, along with its partner nations, set out to build a structure where we might live and work off-planet. The International Space Station, the largest human-made object in space.
I'll call the International Space Station the world's greatest laboratory. The partners are at NASA, the Russian Space Agency, the European Space Agency, Japan, and Canada. So it's not just one nation, not just one space agency. What it is all of us working together. It all had to be assembled and constructed in space. So thank goodness we had the shuttle, because we had large capability to bring the modules up into space.
The station's made out of about 30 loads that went up by shuttle or Russian rockets. And somebody had to bolt it all together. And that's what we did, engineering in space. Spacewalk out there is a great experience. You're hanging onto a bar, like a commuter. And we're just sort of power tool in the other hand. It's an achievement.
When the astronauts go outside in the spacesuits, they do 6 to 8 hours. We kept doing spacewalks, more spacewalks than we had done in the entire history of human spaceflight.
And each time the shuttle's going up to put a new piece on the space station and bring it to life.
Columbia, Houston, comm check.
I was in mission control the morning that Columbia was supposed to come back and land. Capcom was unable to get the crew to respond. When we got a phone call telling us that CNN is showing pieces breaking up over Texas, it made us really understand that we had really just a tragedy on our hands.
What we're seeing here is very ominous indeed. These are pictures which tell the story. That is clearly the shuttle breaking up as it was coming in.
I knew everybody on that shuttle and was close with them. You feel responsibility on the one hand, but also responsibility to understand what went wrong. And then, of course, there was a bigger picture. Should we continue to fly the shuttle? Should we even be flying people in space? What is it that we want to accomplish?
The shuttle was getting very old and wasn't as safe as we thought. One of the decisions was that The space shuttle was not the program we wanted to be using to fly humans back and forth to space on a regular basis. But we took our commitments to our allies and partners on the space station very seriously.
We will finish what we have started. The shuttle's chief purpose over the next several years will be to help finish assembly of the International Space Station. In 2010, the space shuttle, after nearly 30 years of duty, will be retired from service.
The International Space Station weighs approximately 1 million pounds and travels at a speed of more than 17,000 miles per hour, orbiting the Earth 16 times a day. It is home to one of the most productive scientific laboratories in history.
In the course of a year, we do about 400 different scientific experiments on the International Space Station. The zero-G environment is pretty amazing for research. We have all these experiments and we want to figure out what happens to things in space. Most of the experiments that we do are physics, biology, chemistry. For example, fluid physics, or understanding more efficient combustion.
Crystals are able to be grown in space that are perfect. So if you're looking at producing pharmaceuticals, we can better look at the structure of a drug. When you make semiconductors and gravity is overcome, they align themselves perfectly. So you get these really fast semiconductor materials.
The ISS is a closed life support system. So we're collecting our energy with solar panels. That provides the energy, for instance, to take our water and break it into oxygen and hydrogen. We also are losing a lot of water through our bodies from our breath, through sweating and urinating. We collect all that, we process it and make it clean again, make it drinkable. And then the excess of that we use to break apart and make more oxygen. My first flight to the International Space Station was in 2002. I launched and landed on the shuttle. My second flight, I launched and landed on the Russian Soyuz.
After we retired the shuttle, we talked with our partners, the Russian Space Agency, and they have a 3-person vehicle called Soyuz. And we said, okay, can we use Soyuz temporarily to rotate crews to the International Space Station?
We've had this partnership with the Russians for years. It's something we're going to build on, that global kind of partnership. But clearly we'd like to have the capability here in the States. And so what we've done is we've created what we call our commercial crew program.
Liftoff of the SpaceX Falcon 9 rocket.
We reached an agreement with 2 companies, Boeing and SpaceX, to build 2 different vehicles that could carry our crews to space. You know, we have always worked with the private sector. Eventually, NASA will send the crews up through Boeing and SpaceX. They'll dock to the International Space Station and stay for 6 months or 7 months. So we'll do even more research and more science. The International Space Station showed that humanity can, in fact, work together. That in spite of everything else that's going on down here on this planet, when you really focus on a particular mission, you work pretty well together.
This is the hardest thing we ever done. We can build this space station that, in my opinion, is the hardest thing we have ever done. And if we can do this, we can do anything. We just have to dream it and dream big and go do it. And that's this, this perspective you get when you're able to spend time in space and look out at the planet we have.
For almost almost 60 years, astronauts from the Apollo program to the International Space Station have made it clear. The farther we travel, the better we understand home. NASA has shown us that ours is a precious planet.
NASA has unique capabilities because we have the point of view from space. With NASA's carbon monitoring system, you can see the amount of CO2 in the atmosphere decreasing in the spring and the summer. Plants of the oceans and the land surface are greening up and pulling the carbon dioxide out of the atmosphere. And then in the fall and in the winter time, you'll see the CO2 in the atmosphere increasing because plants and animals are releasing the carbon dioxide that was captured during the growing season. There is a graph called the Keeling curve where you can see the summer and winter cycle. The process is very natural. Contrast that with old slow carbon. So this is a chunk of coal. It was also made by plants. It also contains carbon dioxide that was in the atmosphere. But the carbon in this chunk of coal was taken out of the atmosphere 350 million years ago. And since the Industrial Revolution, we've been taking it out of the ground and using it for a fuel.
And release the
burning
carbon
of fossil fuels, whether it's coal, oil, or natural gas, has released this very, very old carbon back into the atmosphere.
Yes.
A lot faster than the oceans and the plants on the land can take it out of the atmosphere.
And very quickly you have to stop with
It's
oil,
bit by bit
benzene,
moving the Keeling curve up.
You have to stop with oil. That is the only way.
1989 was the last time we saw 350 parts per million. And it appears that 2016 will be the last time that CO2 has dipped below 400 parts per million. And what the heck is 400 parts per million? What does that even mean? Well, we know from the analysis of ice samples from Antarctica that before the Industrial Revolution, the amount of carbon dioxide in the atmosphere was about 275 parts per million and had been this way for thousands of years. Something has increased the number from 275 to 400. We're quite certain that that is due to the human activity of burning fossil fuels.
I take these satellite measurements and the variation over time of how the world is changing as facts. We've seen this warming over the last century and a half, very, very meticulous measurements, and it shows a really sharp acceleration in the warming over the last 4 decades.
People have a hard time understanding what's a big deal for a planet that is warmer by a degree or warmer by 2 degrees Celsius. But the impacts that we're worried about are being triggered not at a 20-degree warmer world, but they're being triggered at a 1-degree warmer world.
Over the last decades, we've seen the ice melting. We've seen the ice melting at the North Pole. We've seen the ice melting really fast on Greenland, where it's falling off Greenland into the ocean.
We've had Pacific Islands that have already had to be abandoned because of sea level rise. We can combine our data with global climate models and say, how is sea level going to change over the next 5, 10, 15 years? Because if we continue on the path we're doing, there's going to be a lot of coastal communities all around the world that are going to be flooded.
As scientists, we're just taking the most precise data that we can. It's open data, it's factual. For instance, the enormous droughts and fires that we have around the world are directly related to a warmer planet. That has a huge impact on people. was unprecedented.
If you have a warmer atmosphere that can hold more moisture, because that's what warmer atmospheres do, they can suck up more moisture. That means more convection, more big thunderstorms, more hurricanes, more extreme weather. That's one of the likely outcomes of a warming world. We've built our civilization around the current climate, our coastal cities, our food resources, our water resources. They're all pegged to the current climate, and there's not much slack in the system.
We're already seeing impacts, and impacts are going to increase. In a 2-degree warmer world, there'll be more. And in a 3-degree warmer world, there'll be even more. And when you're looking at those kind of scenarios, 3, 4, 5 degrees warmer, which are totally plausible, if we go down that path, we will be looking at a different planet.